Hi, my name is Marco Gargenta, and today we're breaking open Erlang with its founder, Joe Armstrong. Welcome.
Yeah, thank you.
So we're pretty glad to have you here in San Francisco. It's not every day that you come to a stateside. So what brings you
Well,
to America?
it's the Erlang factory where loads of Erlang users get together. And originally I wasn't going to go, but then I saw there were all these interesting talks, and I thought, I think I'd better go to that and see what's going on. So.
Got it. Any specific talks? Any specific infrastructure applications?
I'm kind of interested in things about large server farms and low energy, and if we can turn them off and things like that. I've heard there's some stuff about that. I don't know. We'll have to keep my nose near to the ground and see what's going on.
So basically power those server farms with Erlang and...
Yeah, I think that, yes. I mean, I think environmental problems would I mean, people have actually been doing what you might call optimally bad things for many years. They've been doing load balancing. So if you imagine a load of servers and you load balance over them, you know, you choose a server with the least traffic on it, and then you never turn the things off. But the biggest power savings have got by turning servers off. So you shouldn't be doing load balancing, you should be doing load concentration. So you really want to switch around loads and turn things off, you know, save energy. So
I was looking at the lineup of speakers for Erlang Factory a little bit, and it seems like that there's an angle to the big data for Erlang, and certainly big data is becoming really hot, and you're talking about the server farms, and there's a whole buzz about that. So do you see Erlang be a good solution for solving the problem of basically crunching numbers across inexpensive hardware, big data centers?
Well, of course you could do that in any language, but Erlang was designed for parallel programming or for concurrent programming. So in so much it was designed to do that kind of thing. It wasn't designed for big data, but it was designed for massive concurrency, and so it's appropriate for that. Yeah, sure.
Got it.
And the other thing you have to think about is if you go to planetary scale computations or very, very large scale computations, you have to make these things self-repairing and self-configuring. You know, you're back to Alan Kay's idea of object-oriented languages where things repair themselves. I mean, I see computations as assemblages of sort of zillions of computations. You send messages, and they break. It doesn't matter. You know, the Erlang failure model is kind of central to all of that.
Yeah. I think it's interesting because many other languages you can also accomplish concurrency and put things in a parallel, and there's certainly solutions for that. But the other half of Erlang is its fault tolerance.
Yeah, I mean,
self-fixing.
The languages they say have got Erlang-like semantics means they mean by that they've got the message passing and the mailboxes and things. They don't mean they've got the error handling and the way the errors are sort of integrated with it. You see, errors are handled out of band in Erlang. You know, you've got the sort of regular things that should be going on, and then you've got the errors, and you treat them completely separately.
Got it.
And that's a very kind of healthy way to deal with systems. I mean, that's how we work. I mean, you don't repair yourself. If I drop over with a heart attack, I can't repair myself. A computer that's crashed can't fix itself. Somebody else has to fix it. Has to observe the fact it's gone wrong, and fix it. So if you want to do fault tolerant computation, you need two computers. You can't do it on one computer. I mean, how can you make anything fault tolerant with one computer? Because if it crashes, end of story. So in fact, you need two computers. This one's doing the work. This one's observing it. If this one crashes, this one takes over. Okay?
Right.
So if you want to do something that's fault tolerant, you need to do both concurrent and distributed programming.
Makes
Now
sense.
that's where we were in 1985 or something like that. So we thought, okay, so how do we program this stuff? Because we were building highly fault tolerant systems. So in fact, my interest is in building highly fault-tolerant systems. It's not in, and concurrency is natural because of that. Now, once you've split things into two machines, that's the basis of scalability. You see, fault tolerance and scalability are ultimately connected. If you have thousands of independent elements, it's scalable. It's also fault-tolerant. So the architectural things you have to do to achieve fault tolerance are exactly the same thing. It's the architectural things you need to achieve scalability.
So your objective was actually to solve the fault tolerance.
Yeah, it was to make fault-tolerant systems. It wasn't to make scalable systems. They then turned out to be scalable as well. And they also turn out to be easier to understand because that intellectual exercise of programming them forces you to think about small units which in themselves can detect and recover from errors.
Interesting.
So in fact, this is the basis of object-oriented programming. as Alan Kay said, the notion of an object is you've got this thing, to get it to do something, you send it a message, and then it replies by sending a message. So Erlang, I think, is the only object-oriented language, and I've been quoted often as saying, well, I thought it was silly. I did think object-oriented programming was silly a few years ago. I've changed my mind, and now I've decided it's a good idea, but I've also decided that Erlang is the only object-oriented language.
Got it.
So Java and things like that aren't actually object-oriented.
Speaking of languages, Erlang has a very unorthodox syntax. So how did that come about?
No, it's got a very orthodox. Other languages have got very unorthodox syntaxes. They're really weird. All these strange curly brackets everywhere. What the heck do they mean?
I know. Okay, that's one way to look at it.
Well, it came from Prolog. So if you program Prolog, you would be very familiar with the syntax. And I mean, can people look me in the face and say Erlang's got a weird syntax and they can write Perl or something like that?
That's true. That's true.
After about a week, you forget syntax.
Okay.
It's like English. You have commas between clauses and you have a dot at the end. That's just like Erlang.
So it is a functional language, and there's the whole rage about functional languages nowadays. So how does it stack up against the other cool kids on the block? Scala, Haskell, languages like that. Closures.
It's perhaps not as religious as Haskell. It's a very pragmatic language. It was built to build real systems. Not that Haskell wasn't built that, but I mean the view of the world is different. The view of Erlang is sort of a world that's always changing. I mean, we put code into a system and we run it, and then we upgrade it without stopping it. That means it will be inconsistent. It might mean you can't do type control or things like that. And it also enables a lot of things which you can't do if you have a strong type system.
So hotspot swappable language, right? That's one of the buzzwords or selling points of Erlang. Where does that land itself well? What kind of applications do you see that's important to actually be able to change?
Well, anything you never want to take out of service. We've seen there's a bank in Sweden, Klarna, which uses it. I think they're one of the only banks that never is out of service. They upgrade their software without taking it out of service. There's not a 4-hour period in the middle of the night where they turn it off to update the database. It just rolls around the clock. And of course, we come from Erlang comes from Ericsson, where we built telephone switches. So it was kind of in the DNA of the organization to build fault-tolerant systems. I was brought up on them, and we used to have this 4 minutes of downtime per year was the spec for the telecom system. And more than that, we paid fines. There was like $20,000 fine if you were down for more than 4 minutes a year. So it's like 4 minutes per year was the base case.
And that's what the 9 nines came
No, but that 4 minutes a year is about 5 nines or
5 nines.
Like that. 6 nines is about 30 seconds a year. So we're hitting about 6 nines at the moment.
6 nines.
The 9 nines was more a kind of, one of our customers said that, and it was British Telecom, and we thought, it's quite quotable. So.
Excellent.
And it was their information, not ours. So we just, that was a marketing gimmick, really. But it's not that it wasn't true, but it was. You don't want to take it out of context.
Got it.
We're not. In my lecture, I'm giving one of my lectures. I said, well, where have we got this idea that 5 nines is difficult? Or you can have 100 nines if you want it. It's an engineering thing. If you have 1,000 systems and the probability that they all go down is 10 to the minus 3, the probability they all go down at the same time is 10 to the minus 300. Sorry, how would I say 1,000? 3, yeah.
So you just need one box up. Pretty good,
yes. Independence
makes it possible.
2 machines, the probability that both goes down is 10 to the minus 3. Probability to both go down at the same time is 10 to the minus 6.
Got it.
Got 3 of them, it's 10 to the minus 9. 4 of them, it's 10 to the minus 12. You can make it 10 to the minus anything you feel like, if the architecture allows them to be independent.
So basically, concurrent systems are always going to have higher fault tolerance than anything else.
Or
lower downtime.
If you want zero downtime, you have to make them independent and with their own power supplies and independent routes through the routers and everything.
Got it.
So it's kind of a good idea if the semantics of your programming language kind of understands that at a deep level. So it's built into it. It's not. So we've been building systems like that for years. We know what we're doing there.
So it is an open source project, but what kind of an open source project is it? How do you guys manage yourself? How do you govern yourself? Is it more like the Linux type of an open source project, more like an Android type of an open source project with a totally different governance internally?
I think to me, the open source in that sense means it's got an open source license. I mean, we haven't really talked that much about the governance. That's now becoming more interesting. I mean, it's been Ericsson who's open sourced it, and we've taken in contributions, which, you know, have greatly improved it. How it's going to go in the future is something we're discussing at the moment.
Okay. So do you have actually a network of contributors or people who are pitching in the code?
Yes.
Got it. Okay. So it's pretty. And what about the roadmap? Is there like a public roadmap, or is it whoever needs whatever they need?
There's a formal procedure. There's a EEPs, Erlang extension proposals, and they're kind of vetted. But to the extent that which the main development is funded by Ericsson, it's Ericsson who takes the final decision on which of these EEPs to implement themselves and to concentrate on. So I think it would be nice to kind of open it up and possibly finance some of these ones which Ericsson might give a low priority to, but external users might give a higher priority to. I mean, we tend to prioritize the ones which we have commercial use of. But
So how does Ericsson fit into the picture now, given that they open sourced it, but seems like they're still controlling now the roadmap going forward?
Well, you see, we use it so much for our internal products. I mean, we've got hundreds of Erlang programmers, and we have. I don't know the percentage of the world's mobile networks that are controlled by. If you're using an iPhone or an Android phone in Sweden, you know, all your data traffic is controlled by Erlang. I mean, it just wouldn't work without Erlang. I don't know about America what market penetration Ericsson has there, but we're controlling 40% of the world's mobile networks for 3G, GPRS, GSM, Edge, and we're controlling 60% of the world's networks for 4G. So every single IP packet is controlled. The most reliable part of the system is being controlled by Erlang. That's the bit that really has to be fault tolerant, otherwise your mobile data wouldn't work. So we're controlling about 60% of the 4G total world data networks, and that's an internal product. So we've got hundreds of programmers working on that. So the OTP group is fundamentally supporting them. So if they said, well, we want to change to the language that moves it in this direction, they're going to get the priority because they're the people who pay for it. And it's not that we are unwilling or unresponsive to people on the outside world, it's just they're not paying the developers to do that.
Got it.
So if we could refund that and focus it into those, that would be fine.
Okay, so the economics of the languages are such that most of the development happens within Ericsson.
Yeah, I think, yes. I mean, it's kind of he who pays the piper calls the tune. So they're paying the most amount of money for development. On the other hand, I mean, we're perfectly happy to give commit rights to people who've shown themselves to be responsible and so on. I mean, that's not an issue. There are people outside Ericsson who have commit rights to the Git archives and things. They don't need to get stuff approved.
So it's a standard sort of Linux type of level. You become a committer at some point.
And Björn Gustafsson, who's the main developer, I mean, he's sort of. We welcome bug reports, and often people patch things themselves, but then Björn looks at it and says, well, it should have been done that way instead. So he fixes it up.
Got it. So
I mean, we want to have a good relationship with
the developing community.
Yeah.
And I imagine that's one of the reasons for Erlang Factory, right? Basically
it's just to get everybody together. And also there's a kind of mutual, you know, you get a bit of, the enthusiasm keeps you going for a few months, and it's kind of like a vitamin injection or something.
Got it.
It's just good fun.
So I was looking at the adoption of Erlang worldwide, and it seems like, of course, it's big in Sweden.
Yeah.
But it's also big in places like Russia and China. How about?
I really don't know. I mean, you're telling me that, and I know that I see a lot of blog articles in Russian, and I click on translate, and
it's very interesting.
So I know there's quite a lot of activity there, but I don't know any details.
It's very interesting.
They are sort of separate worlds, I think. You know.
So do you see it globally growing, shrinking, being steady as a adoption of the language?
It gets to a point you don't really know. I mean, we're seeing all the kind of second wave things happening now. You know, stupid questions on the net, and a lot of books now. So Francesco wrote. There's an O'Reilly book,
the
pragmatic book.
No starch, yes.
Yeah, and then O'Reilly's come out with another one, and there's Oh yeah, there's the Learn Use from Erlang for Break.
Good, yeah. That's a good book.
And then there's a second generation book. The books about applications are coming out. And then we've got companies like Basho doing React and what do they call Ops code doing the Chef 11, which will be controlling Facebook and things like that. So they're kind of good signs.
Yeah, I was doing a little bit of research, and I found that Erlang is now in places like web applications, which is not something you expected to see, and in places like big data, which I did expect to see because of its concurrency, but not so much because of the fault tolerance.
I think what isn't a surprise to me, but is a surprise to other people, is say the expansion in games, because a game looks very much like a telephone exchange to me. I mean, it's just, what's a telephone exchange got? 100,000 people simultaneously connected to one node, just sort of sending a bit of signaling. Then from the computer's point of view, they signal a bit and then sleep for a long time, and then they signal a bit. So you need very fast context switching. You need to keep them all in memory. You don't want to go out to a database or something. So, our telephone exchanges we built, maybe we dimension for 100,000 sessions per CPU or something like that, and we don't have external disk databases. It's just all in RAM, and we need to protect all these 100,000 users against each other for software errors. So how's that different to a big multi-user game? It's not. It's the same architecture. But it kind of comes as a surprise, if you've been doing it a different way.
So what were your personal goals when you started the project? What did you hope to get out of it other than fault tolerance?
It wasn't. It's like, there's a lot of programming languages that never started as projects to build programming languages. This was just actually, I got a job at the labs to work on just ways of improving how to program telephony. And there was a tradition in Ericsson of building things. So this kind of duplicated processor, fault tolerant, you've got to change the code on the fly, it's never got to go down. That's in the DNA of the organization. So when we're designing Erlang and talking to it, we had the guys there was a guy, Seba Torstendahl, who had done Eri Pascal, and that was Pascal with concurrent processors. And of course, he'd learnt that from Jørgen Hemdahl. Jørgen Hemdahl had designed the first system. I think Jørgen Hemdahl could almost, he sort of independently invented object-oriented programming, although he's never credited with that. But just this notion of fault-tolerant blocks of things sending messages to each other and them being inviolate so they couldn't crash each other. That was built into hardware in 1974 by Ericsson. And then you have to remember, Ericsson's been building large network computers much longer than the internet. The worldwide telephone networks have been running for 20 or 30 years before internet. So I think the telecoms guys actually knew, which I sort of call myself a telecoms guy, we actually knew how to build worldwide networks years before the computer people. And then the computer people kind of rushed in and to us were just reinventing stuff we already knew about. Although we were selling into mass markets with small numbers of customers. So before the deregulation of the telecom market, a company like Ericsson would have 3 or 4 customers per country. Well, no, they'd have one, the PTT of that country. And then you had deregulation, and you have 4 or 5 customers. Ericsson's big disaster, of course, was selling into the mass consumer market, where they made handsets, telephones.
Sony Ericsson, yeah.
Yeah, and they joined with Sony Ericsson. But you see, they had a marketing organization that could only deal with large infrastructure products, not with small consumer products. So now it's finally sold off. So, Ericsson's very good at big infrastructure. And Erlang was designed for big infrastructure, and it took the kind of history of the languages before that to grow upon.
So as a paradigm change, what do you see as the kind of like the crown jewel of Erlang? Would it be the message passing, the way of communicating between processes?
Oh, messaging is the big thing. Yeah, I keep going back to what Alan Kay said. The big thing about object-oriented programming was the messaging, and unfortunately, he said, people are concentrated on the lesser idea. The lesser idea was the organization into objects and methods. That was a lesser idea. The big idea was the messaging, and in fact, it's a big idea in Unix. The notion of the pipe, the host pipe,
right,
which essentially decouples the source and the destination. That's the big idea in Unix, and in fact, why the internet works. You've got all these pipes, just data flowing. What's wrong there, of course, is this all these RFCs using text-based languages. well, the HTTP protocol, for example, I mean, it goes back to the simple message transfer protocol. I mean, it still sends sort of SMTP said subject something and then text something, and it said 200 OK. Well, you can find that 1,700 RFCs later in HTTP. It's much better if you can communicate in something that's got a generic parser. So if you communicate in XML or JSON or something like that, you don't need to have a text specification. And it's even better if you can formally specify what's in that contract. I mean, I'm not saying JSON's a good language, but it's better than text language. Actually, languages are better than JSON, but the world's probably not ready for them yet.
So message passing and a really efficient way of processing those messages, right? That's one of the things.
Well, I don't care about efficiency because I mean, all efficiency has come from clock speeds and parallelism. But I do care about correctness, so I go back to Koenig and Plauger. You know, first of all, they say make it right before you make it fast, and then they say make it beautiful before you make it faster, and then keep it right when you make it faster. So, I think the big problem that's always interested me, and the problem of fault tolerance, is actually how we write software that works. I mean, most software doesn't work. I mean, it's awful.
Right.
You know, you get these things, you can't connect them together. So, in fact, I'm proposing models of software where normally you just have a client and a server. I think you need a contract checker in the middle. You know, this guy who's independent, who's sort of watching all this stuff and saying, are we obeying all the invariants? We just don't take black boxes seriously, if you like. I mean, I think the trouble with when computer science is taught is that all things aren't equally important. You know, if you see a set of bulleted points on a blackboard, on a slide, they're not all equally important. I think I should have a patent on the idea of just having a bigger blob for the important points. You know, so I'm always sitting at lectures and there's some guy sticks up some bulleted points and there's like 12 points there, and I say, excuse me, which is the important one? Oh, it's, you know, number 4 or something like that. Well, how am I expected to know? So when we teach computer science, it's very difficult to know what's important and what's not important. And if I were young and learning it now, I would be in a state of complete confusion. I mean, I've had the privilege of learning this stuff as it came along. So for me, you know, learning object-oriented programming or functional programming or something like that has not been a big step or a difficult thing because I've had many years to assimilate the ideas. But if you're just going to learn all that stuff in a 2 or 3 year period and then be faced with a plethora of choice and a sort of marketing campaign that's got nothing to do with technology, it's just, you know, use us, we wash brighter. What the heck do you do? How do you decide? Very, very difficult.
I mean, you're right. You know, studying Java in college, I remember it was all about basically how the objects are organized and what inherits from what and what is, you know, how they're related to one another as opposed to how they actually communicate.
And then a lot of things like the study of algorithms and you know, basic computer science are perceived as being too difficult. You know, the programmers don't have the kind of computer science graduates. I know they dropped the Dragon book from some courses because building a parser or something from first principles was too difficult.
Yeah, exactly.
But I mean, this is the craftsmanship of programming. This is the stuff you've got to learn. Now, I had the advantage of being able to learn it over a many-year period, so I didn't have to do it all in 2 years, which would be very difficult.
So we talked about, you know, concurrency, and we talked about fault tolerance, yes. the two halves of Erlang. There's the third half, the OTP.
Yes.
And to some people, that is a very important crown jewel of the system. So can you tell us a little bit about
well, that's like, it's got perhaps an unfortunate name, because the name...
Telephony.
Yeah, I mean, it's a kind of funny name. I think if you thought of it like C and Unix, you know, C is the programming language, Unix is the operating system.
Okay.
So you've got Erlang, which is the language, and you've got OTP, which is a large set of libraries which give it sort of middleware properties. So OTP was actually designed for building projects with big teams. I mean, it was built for... It was a third generation. It had been used twice before, and it was a third rewrite. And it was done for the Ericsson AXD301 project. And the idea there was, if we had about 60, 70 programmers in that project. So if you just start off with Erlang, you could make your own way of building a client server, or you can make your own way of making a sort of rotating log or something like that. And we thought it's not really very good if 60 programmers all invent their own way of building, say, a client server model. So we said, okay, so here's the standard client-server model. Please, would everybody kindly go and use this? And here's the standard way of doing errors and things. And we built 7 abstractions. For example, supervision trees. We build things into trees, and it's a worker manager thing. You have a manager, hands out jobs to workers. And if the worker dies, the manager gets informed and can restart the worker. And then we just said, okay, there are 2 types of trees. I mean, there are independent tasks. So we've got independent tasks. If any one of them dies, it can be restarted independently. And then we've got dependent tasks where if anyone dies, they're all dependent upon each other. So the only thing to do is kill them all and restart them all.
So state versus stateless.
Yeah. So we've got and trees and or trees.
Okay.
The one. And then we said something, and we realised that, well, if something fails and you restart it, you don't want to get into a loop. It might happen that if you restart it, it'll fail for the same reason again. So we added restart frequencies and things. So you can say, well, if you've restarted it more than 5 times every 6 minutes, or 2 times every millisecond, or 400 times every 3 hours, I mean, whatever you feel like, you put this in. And then if the manager has done that number of restarts and it exceeds that, then it itself dies, and then the guy on top of it sort of obeys these rules recursively. So finally, if the guy right at the very top dies, you're screwed. And these were all very pragmatic. I mean, when we started, we didn't have these supervision trees and things. We thought, well, that's the kind of abstraction that's useful to use. And so there's a lot of experience baked into them, and there's a lot of products that have been used building them. So if you're starting your own project and you hadn't thought about it a long time, you say, wonder, well, okay, so use the OTP libraries as a first cast. It's probably better than the one you would do yourself.
So basically,
on the other hand, if you were really expert at that, you wouldn't necessarily use them. It's like any. I think I notice the point about using an abstraction is you need to know what is being abstracted. And if you ever lose that, if you ever go back and say, well, I'm using an abstraction, but I don't know what it is that they've abstracted, then you're screwed. Right. And unfortunately, I think we are getting people who are just using abstractions, just pulling them off the shelf and using them, but they don't know what it is that we have abstracted. And then if it doesn't work exactly how they thought and they have to tinker around, then they go into panic. It's just like, open up the black box. Oh my God, do I have to open it up and see what's inside?
Got it.
And it should, if we've done a good job, then we will be able to use these things as black boxes without opening them up. And if we've done a bad job, then they won't. And I hope we've done a good job there.
So what does it take for an average C, C++, Java developer to basically adopt and start working with Erlang on a project and even consider it for a project?
Buy a decent Erlang book and
go through that.
Turn it open at chapter 1 and start typing the programs in. I mean, that's the only way. There isn't a
do you think the learning curve is steep, or how would you compare it to other languages and frameworks?
You can't. I don't know.
Yeah.
I mean, all programming is difficult to learn, if you ask me.
Yeah.
You're always going to have. I noticed years ago. I gave a Prolog course, and I was teaching Prolog, and we had question and answer sessions, and I decided I deliberately wouldn't solve any of the. I wouldn't be like hand out the teacher's answers. I would do them in front of their eyes, and so I was trying to solve these problems in front of their eyes, live coding stuff. And one of the students said something which I thought was very interesting. He said, "You make exactly the same mistakes as I make. I mean, in logical thinking." He says, but it's very encouraging watching you, because what I notice that you do is you correct them much quicker. And I noticed that. So once you're good at a language, you see the errors and you correct them very quickly. Doesn't mean to say you don't make all the same mistakes. The beginners don't really see that. Yeah. They sort of, whoops, it crashes. I mean, when I'm writing Erlang, whoops, it crashes. I just, that, and I correct it quickly. That's just experience. But I still make the same algorithmic errors as everybody else does. So I don't think programming is. The difficult bit is actually not in learning the language or its semantics. That's pretty straightforward. It's in knowing the library structures, knowing which libraries to call.
And it's about.
And that's the same in any language. If you look at something like Smalltalk, you can learn Smalltalk in an afternoon. The syntax is really easy, but it'll take you like 3 months before your head can sort of take in which classes are important.
It's basically about wrapping your mind in a new way of thinking about things.
It's also, I mean, I talked to Dan Ingalls about Smalltalk and said, well, you know, can you tell me which are the important objects in Smalltalk? And he says, well, it's object, and something, there's 4 or 5 of them. I mean, when OTP starts, it loads in 62 modules or something. Only about 4 of them are important. You know, error handler, init code. I wrote quite a bit of that stuff, you know. So I know, but what happens if you're a beginner? Start it, 67 modules come in.
Yeah.
My God, where do I start looking? You know, it's difficult. But that's true in any language.
Yeah, or any system for that matter, yeah.
So I've one of my slides, I'm going to talk about this this week, is about the complexity of systems and what we can do about it. So kind of formulating a law. Joe's law was Joe's second law or third, I can't remember which, but all frameworks grow in complexity to the point where nobody can use them anymore.
That's true.
It is. You look at these, you know, things like Xcode and, my God.
They become beasts,
awful,
monolithic beasts.
Awful, you know. I mean, I'm not particularly nasty about Xcode. I'd be just as nasty about Eclipse or something like that. But it's just the complexity there, and that user. You know, have you read these books on programming by Stevens? You know, network programming and TCP illustrated volumes 1, 2, and 3. What Stevens did in his book, and what I try to do in my books, is actually describe small fragments of code. You describe these little idioms. You know, there's 5 lines of code. You know, which when you glue them together in different orders, you write beautiful software. You know, it's like learning cooking. You need to know, you know, what salt and sugar and what it does to the flavour of something. So it's the same thing for programming. You need to know what these few lines of code do.
Got it.
But if you're in a hurry, you just Google, how do I do this?
Or you post to Stack Overflow.
And you whoomph, yeah, and you cut and paste 10 lines of code without understanding what it means.
Yeah.
I mean, you can see the kind of more popular languages, the worse the examples are. For example, if you, I mean, not that I wish to, well, I suppose I'm going to be nasty about PHP, but if you look at perhaps not PHP, but the examples you see are terribly formatted. You know, they're not neatly indented. You know, they're just kind of cut and paste this in. And, you know, when you start seeing code that's badly formatted, which is out of context and downright wrong, you know, then you know you're becoming popular. So we're beginning to see that.
I think JavaScript is at that level right now, so.
JavaScript is I sort of have a love-hate relationship with JavaScript.
Lots of people do. I think that's the
I mean, the lack of a concurrency model is, I was writing some JavaScript just before I came, you know, and I thought, my God, you can't do synchronous I/O. You've got to do asynchronous I/O. Go read this, and when the read is finished, go do
Call
this,
back.
and when the thing is that. So how the heck, since you don't have processes, all the concurrency has to be put into one thread. And God knows what you do if you get an error. You know, how do you sort of untangle this sort of spaghetti stuff?
Yeah.
I mean, it's like this, I think it's rather funny because, you know, something like jQuery? It looks very easy. It looks very nice because you say, okay, so I've got a div in HTML, div A, on click, execute that function. Hey, that's really easy to understand. On click, do that. Yeah, that's really easy to understand. But the consequences of putting lots of these all together become something that's not easy to understand. So you see, there's a relationship between the primitive things in a language and the constructions that you can build in a complex thing. If those primitive, it's not apparent that if you choose the primitive things incorrectly, the big thing will be difficult to understand. Now, of course, this doesn't hit you in the face if you're only building something that's very simple.
Right. Like
but it does hit you in the face when you're building something complicated.
Right.
So they say, you know, like, I see sort of joking, they say, well, you know, in PHP or something, it's really easy to do simple things, and it's impossible to do difficult things, or it's very, very difficult. You say in Erlang, well, it's kind of difficult to do easy things, but it's kind of possible to do really complicated things.
Got it. So it's the right tool for the right job,
Yeah,
right?
sure. And I would never recommend using Erlang for something that's inappropriate. I mean, you know, it's good at what it was designed to be good at, which is like most technologies.
So what are your hopes, personal hopes for the language? Where do you see it going? I'm just kind of surprised it's still there as it is. You know, I've given up years ago, I suppose, if it hadn't.
just like to influence software. I think it'll, whether it's still being used in 20 years' time or 30 years' time, I have no idea. I think it'll be one of those languages which has influenced a lot of languages.
Mm-hmm. Like small talk? Or
Yeah, small talk was a sort of, had influenced an awful lot of thinking that came after it. I think I'm quite pleased that Erlang has influenced how people think. But I think they haven't got it yet. You see, one of the things that I go on about is what do you call it? Accidental and inherent complexity. So accidental complexity is complexity that comes from the way you've decided to solve a problem. Mm-hmm. And inherent complexity, that's just the complexity that's in the problem itself. So if you have a parallel problem and you write it in a sequential language, then you introduce accidental complexity. Now, people don't realize that, because if suppose you've got a parallel problem and you solve it in C++, you're going to use possibly operating system process, you use semaphores and mutexes and message channels and things like that to solve it. Mm-hmm. And that's a mess. Oh, it'll make your head hurt. You know, as soon as it gets complicated, it's really horrible stuff. And then you say, well, okay, let's try and do it in Java. But wait a moment, you've got the same abstractions. You've still got synchronized methods, and you've still got mutexes, and so it's a mess as well. And then hey, let's do it in Ruby. Okay, so we've got synchronized methods, and So then you say, oh, all this parallel programming stuff is tricky everywhere. But it's not. Those are all accidental complexities. If you do it in Erlang, it's really easy.
Right.
But you've got to think differently.
Yeah, yeah. I can see that.
And it's like, I'm going to start, I'm giving I hope people from Lambda, you're not, if you're going to go to Lambda Jam in Chicago, don't turn your camera off now. I've got the start of my Lambda Jam lecture where I play them, I'm going to play the start of Mahler's Fifth Symphony, you know, and show the score, because this is a parallel program. You know, and it starts da 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 da, and it's got 16 instruments playing in parallel. So the score is shown. This is a parallel program, a musical score. You know, you've got the trumpets and the violins. It's also a fault-tolerant score, because you've got, you know, the first violin. It's not one violin. It's 10 violins all playing at once. Can you imagine what music would be like if it was sequential? Can you imagine Mahler? You know, how would he write his symphonies? Would you go to a concert where they play all the trumpet, all the timp? You wouldn't.
Right.
You know, we're losing, when you try and describe things that should be described in parallel, like music, in a sequential language, you introduce all this complexity. It just becomes impossibly difficult. So you take a web server, Apache or something like that says, okay, the operating system thinks I've got one process with 10,000 users. An Erlang web server isn't actually like that. It looks the same. But the abstraction is I've got 10,000 web servers. So, I mean, if you're thinking about a web server in Erlang, say you use Cowboy or something like that, people don't get this, you see. As I see this Cowboy system, I'm thinking my machine's running 10,000 web servers.
Right.
But you see, they don't see the difference, because they just see the external behavior. It's controlling 10,000 things. But actually, you look at it in detail, it is actually 10,000. If it were an operating system, we would see 10,000 little processes. Inside Erlang, you see 10,000 little processes. They're all independent. And that means if there's an error in any one of them, it doesn't affect the rest. Look inside Apache. It's not like that. The operating system, one big process. Inside Apache, one big process. And that's why, if you want to do, say, a PHP plugin, it has to spawn an operating system process to do that. And that's a very expensive process. I mean, operating systems don't handle thousands of processes. They handle a few,
hundreds.
Yeah, hundreds, hundreds, thousands even. Tens of thousands were a bit shaky. Millions? Forget it.
Yeah.
And so that's what the games, the Wonga games people were giving a talk about Erlang. And they suddenly said, hey, wait a moment. The current model they had, we've got the user session and the game data is in a database. So every time a user does something in the game, they've got to go and access the database. So the database became the bottleneck. But wait a moment, most of this is just state data. It just belongs to that game, no other game. Keep it in memory. Keep it in the process associated with that game. That's exactly what we would do with the telephony transaction.
Exactly.
It's no different to a telephone call. You know, when I pick up my mobile and I call somebody else, all the transient state of that in the Ericsson exchanges, that's in a process. It's not a database. Yeah. It's not a database on disk or something like that. It's in memory in a memory protected region.
And it's so much faster that way.
Yeah, sure.
Yeah.
Yeah.
Excellent. Well, thank you so much for your feedback on Erlang. We're glad to have you here in San Francisco.
Thank you. Yes.
And I hope you enjoy the Erlang Factory this week.
Sure, I will. Yes.
Hopefully, we'll see you there.
Yes.
Thank you.
Okay, thank you.